welcome.
Hola. Hola. Gracias. Hola, gente. Me llamo Isa. Soy de Brasil. Pero pido disculpas por no hacer esta charla en español. Es muy malo. Ahora voy a cambiar a inglés. Relief. Wow. Okay. So hi, I'm Isabella Silveira. And today we're going to talk a little bit about machine learning and how we can actually make art using our computer machines. So firstly, I'm going to start by doing some storytelling. Does anybody know this guy? Yes. So Art Attack was basically my whole childhood, and I was very into doing things on my own and being creative. And this guy, he was amazing. He would just get a bunch of clothes and just lay it on the lawn and do these amazing things, or get a bunch of salt, put it on the floor, and he would get these amazing drawings, and it was pretty mind-blowing. And it was pretty much whatever I wanted to do, but you can see that I was a very creative, artistic child back then. So if I would try to replicate that, basically what you would see is this. So actually, my mom is here. She's watching. She's among you guys in the audience. So if you want to do some background check, you can totally ask her. Actually, I very casually found out that Sunday you have your Mother's Day. So thank you. I'm going to have to buy her another gift. Thank you, all Argentina. So yeah, I would express myself just drawing, doing all these kinds of things. And nowadays, I'm still able to express myself artistically, mostly through dancing. For those of you who don't know, I actually was in the Olympic ceremonies dancing. I was one of those green things. And because of that, I was able to appear in international television for 5 seconds, which is already a pretty good accomplishment. But nowadays I do coding. I'm a software engineer, so my only means of artistic expression are pretty much through coding. So that's how I get to teach my computer how to make art. And you're probably wondering, what the fuck, Isa, what do you mean? But I'm going to tell you in a little bit. So hi. I'm Isa. This is my one true talent, in case you're wondering. I'm sorry, Mom. And I'm a developer at Working Co, and I'm all these other things. Carioca, by the way, is people who come from Rio, which is where I come from. And let's begin by talking about art. What do you guys think is art? Because it's a pretty discussable thing. So there's not really just one definition to it, so I got 4 of them. So the first one is a dictionary definition. It's basically the most down-to-earth one. So it's pretty much the quality expression of whatever is beautiful or appealing to the human being. But Paul Gauguin said that art can be either a plagiarism or a revolution, which I think is pretty much what goes on. Georges Seurat said art is harmony, which I also agree. And my personal favorite was by Leo Tolstoy, and he said that art is just basically whatever you are able to make some other person feel what you were feeling while you were making something, some means of expression. But does it have to be beautiful or original? Does it necessarily have to have those qualities? Or does it have to be complex or have be one of those artworks that are sold in ridiculous fancy objects, or does it even have to be made by an artist? Because, well, one example of artworks is just basically something that a person has an idea, but sometimes it can be created by someone else. And a little example that I like to show about that is this beautiful work by Joseph Kosuth. It's called 1 and 3 Chairs, which I got the pleasure to see in MoMA in New York. So basically what happens is that you get into the museum and you see this. You see a chair, you see a picture of a chair, and you see a definition of a chair. But Kosuth really didn't make any of these things. He didn't make the chair, he didn't take the photo, he didn't write the definition. So where is the art really? Where's the art part? We're also going to get there. So going a little bit to machine learning, which is probably the part that you're all most excited about. What is really machine learning? Because it's basically this very buzzwordy thing going on at the moment. Everyone is talking about it. Everyone's sort of theoretically doing something with it. But what is it really? well, we can define machine learning by an application. No, it's fine. Let's keep it simple. It's basically something that allows your machine to actually learn. And by learn, we mean like we no longer have to like code this very long switch case scenario with tiny rules for each of the conditions that we may run into in our algorithm. We can just feed examples to machine, like feed things that we expect to happen when they encounter some sort of input. That's what we call training, and the machine is just able to understand what it's supposed to do by those trainings. So you can think of it in a very generic way as it's a tool that is, we're able to use it on our machines just to be able to feed a bunch of raw data, like a bunch of numbers, or you can think of it like a JSON file, and the machine is just able to draw conclusions about it automatically without us having to actually learn every bit of step through it. And there's several kinds of algorithms to each kind of problems. For example, like you have classification algorithms in machine learning. So for those ones, you can use like decision trees, and for prediction, you also have like a different set of algorithms that you can use. And to this one today, what we're gonna do is to generate new art images from previously existing artwork. And for this, we're probably going to need all these things. We're going to start with the, well, spoiler alert, the most important one is the 6. But we're going to start by the powerful algorithm. So for this one, I decided to use deep convolutional generative adversarial networks. What the fuck? So yeah, like the name is really long, I get it. But basically, it's just an algorithm that's capable of generating new images from actually existing ones. Like we're just gonna feed him a bunch of images, and he's gonna spit out something that's inspired by, or like it's like a mixture of all of them. And to do so, we're going to use 2 convolutional neural networks. Convolutional neural networks is an algorithm that is really good for image problems. As I said, like every sort of problem has a most suited algorithm, and the CNNs, how we call it, is ones that's more suited for image problems. And we're just going to put them to fight, basically. Well, eita. Eita in Portuguese means like, what? So what do I mean by fighting? Baby steps. Let's keep it simple. Do you guys remember the algorithms? Basically, we're just gonna have one algorithm that's based on a specific model. A model is basically like a mathematical formula. You can think of it that way. Like it's a way to solve a specific kind of problem. For example, if you want to find a parable, you're probably going to use Bhaskara. As if you want to find the acceleration of a car, you're probably going to use Torricelli. And for these algorithms, we can use a discriminative model, which is basically a model that is really good into identifying patterns or classifying and finding things and recognizing objects in images. For example, if I give a generic image and I ask our algorithm if it can find a duck in it, he'll be able to tell us that. And there's also the generative model, which is a model that is really good in creating stuff from what we're going to feed in the training process. And for these ones, we're going to use both of them, and they're going to interact with each other. So to illustrate that, I have this very nice and legalized example. So we're going to, for example, generate images of IDs. So our first neural net is a discriminator. You can think of it like the bouncer at the nightclub. His job is just to basically recognize if an image of an ID is really how an image of an ID should look like. He's just really good at identifying that. And the second one is the generator. You can think of it like yourselves when you were 16. You're probably trying to like create the images and keep it as real as possible and getting like examples from actual IDs. His job is just going to be creating those images to try and trick the discriminator. And we're just going to put them to interact and to fight and to improve each other. So at the very beginning, they're very bad. They don't do any of these things very well. So what happens is, like, we're going to feed a very lame image of an ID. Our discriminator algorithm is going to probably tell us, no, yeah, that's super legit. And we're going to step in and say, like, hey, no, look at this actual ID. Look at all the things that you're actually missing. Like, it has to have a signature, it has to have a picture. Then it's going to say, yeah, well, you're right, it's totally fake. So that input is going to go to the other neural net, and that's a round 2. The round 2, you can think of it as, like, we're going to feed him a lot of numbers, if you will. It's like a data source. And the reverse deep convolutional neural network is going to take that and generate a slightly better image of an ID. And that process just goes on and on and on and on until both of them are really good at what they do, because they're just, like, continuously leveling each other up. So this is actually what makes it possible to create all these images of bedrooms. None of these actually exist. They're just generated by a machine. This image was actually on the paper where Alec Radford first proposed this algorithm. And it's scary because, like, if you think about it, I would be totally okay in finding any of these images on Airbnb or maybe Booking.com, but none of these exist. And it gets even creepier. Like, you can get all these faces that don't actually exist. They were all generated, and even creepier, because this has a lot of details, but these people don't exist. They're all part of an experiment by NVIDIA. They just fed, like, a bunch of images of celebrities, and after, like, a lot of time of training, the algorithm was actually able to spit out these both people that do not exist. And you can, for our experiment, I built it heavily on top of this implementation, which is really good. You should definitely check it out. So for the second part, we're going to need a couple of thousands of paintings, because for image algorithms and machine learning, you actually need a lot of input. It's not just like a couple of hundreds, you need thousands. So what I did was I made a crawler into this website just called WikiArt. So my first intention was to get everything by Picasso, because I really wanted to see what it came up with as aesthetics, or if it was going to feed me something that's similar. But the bummer is that there is actually just not much more than 1,000 paintings, which is really not enough for machine learning algorithms to work. So the plan B was to filter by genre. So that's where I got the idea to actually filter for landscapes. And I was able to get over 20,000 images of landscapes, which for machine learning, it starts getting very decent in terms of numbers. So what I basically did is I saved all of them in this directory. I also need to set, like, the data file, which is going to be like the zipped version of everything that I had. This is what we're actually going to feed in the training. NPZ is a good format because it's a lossless compression method for zipping things. And you have to specify the size, which in my case I specified to 64 pixels by 64. Fun fact, this algorithm doesn't work with images larger than 256, because other than that, it starts becoming like noise for the algorithm. So it starts getting complicated, and you don't really have any significant results from it. So I just defined 64 because all I have is this machine, and I can't really explode it because I also use it for work. So what you're going to do is you're going to run this command on the terminal. So basically specifying getting all of these values that we already set before. And what this is going to do is it's going to prepare all the images that we previously saved from WikiArt. It's going to, like, cut them into 64, and it's going to save it for us in that file. So now that we're done with the preparing part, we really need a mighty processor for the whole training part, which is very heavy on machines in general. Actually, one thing that you can actually do is try to do the training part in the cloud, for example, is something that people are really doing at the time. But in my case, I use CUDA, which is an acceleration unit by NVIDIA. It's really good because you can get to use, like, the GPU and all these sort of things for improving your algorithm performance. And in my case, I have 4 gigabytes of GPU, which is doable. It's not great, but it's doable. So these are actually the most important part because machine learning is really cool when you see the results, but it takes a lot of patience because like you can literally spend hours and hours, even days running the same algorithm. Also persistence because things don't actually fall into place like as fast as you expect. And love because otherwise none of us would be here, I guess. I hope so. And so for the training part, which is the most exciting one, I guess. All we're going to do is get that prepared data set that we've built in the last step and define the output folder where we're going to get our trained model and everything, which is we're going to later on use on our website. And basically, we're going to run this chainer. Chainer is a library that's really interesting. It's a framework in Python for machine learning that's very interesting because it already has an implementation of this algorithm. And what we're going to do is just we're going to feed all of these images for the framework to train them. And for my case, the whole training took 16 hours, which is it's really not a lot in terms of machine learning. And in the beginning, the images that are generated, because they're still being processed and stuff, they pretty much look like this blur. But later on, you can actually see that they start falling together and start looking like actual things. So I had to stop the execution of the algorithm to make some adjustments and like, because most of the time, if you see that there's like a huge blur or something that you can't really understand, you need to tweak some of the weights in the neural networks. The weights are basically the algorithm's way to interpret whatever you think it's more important. It's like you giving priority to the algorithm by saying like, hey, I want you to prioritize color, for example, or I want you to prioritize some other things. The thing about machine learning is you don't really know what it's doing. It's pretty much like a black box. So you just have to sort of like try blindly to adjust it. And at some point, it really falls together. It falls into place, but it takes a while. So after we have the trained model, what we're going to do is we're going to sort of like translate it to Keras, which is another library, really interesting library for machine learning in Python, because Keras is actually compatible to TensorFlow.js, which is what we're using for this experiment. And by translating it to Keras, we're able to get it compatibly working in TensorFlow. So the important part for us here is just getting this TensorFlow part model, because this is actually going to spit like a JSON file for us, which we'll later on be able to configure and set in the index.js file. You're going to take a look at the code and you're going to understand it better. But this is what we're going to tell our JS algorithm to, hey, this is a trained model. You're going to get all your answers from here, and you're going to match it to the images that I'm feeding it. And the result is pretty much like this. We are able to run it on the browser, which is one thing that is really cool about TensorFlow.js, because it's what it brings to the revolutionary part is the fact that we're able to write machine learning in JS, which I think it's the coolest part because it's really keen in access democracy. I mean, people no longer have to learn Python or R and able to do machine learning. You can just stick to the language that you're most comfortable with, and let's face it, like we have a majority of programmers that know JavaScript, which used before to be used in the browser just for web things, but now we can do all these great things using Node or just JavaScript, plain. And the other very cool part is that we're able to make dynamic machine learning. For instance, if I have the trained model, I don't really need to send any response for the backend to process something, and that takes a while. We can just process it on the client side or have a more lean way to do image processing in machine learning. And the conclusions that I got from this experiment are these images. I was to generate all these images from artworks derived from landscape. You can see that, well, you can't really understand what none of them are, but at the same time, like, if I saw any of these things at a museum, I would really believe that there was some amazing artists behind it. And I was able to get 84 64 by 64 generated art samples. And I noticed that there was a high variance of quality in each artwork, in the sense of there are some samples that are more distinguishable than others. I think that comes from the fact that this algorithm is still sort of like stuck to the definitions of what's right versus what's wrong, rather than actually learning like an art style or a painting style. But that's very interesting as well. And some painting styles are very hard to reproduce. For example, I tried running this algorithm with mythology-inspired paintings, which is definitely impossible because, like, in just mythology alone, you can have Greek mythology paintings, you can have Nordic, and all of them have pretty different thematics. So what I found out is that if you have like art that have least variance in styles, for example, if I ran this experiment using still life paintings, the result would probably be more distinguishable. So yeah, some styles for paintings and art are very hard to reproduce. You should just try to focus on the ones that have like most things in common. If you want to see something that's like resemblance to what you actually fed to the neural network. So stitching the points, I think we have to get used to a future where machines can also do creative work. Because like when we talk about machine learning, we have this thing of saying like, yeah, it's fine, but machines are really good at calculating things, but they're not good in creating. That's just us humans. Well, we're reaching a point where that's not actually true, because like we get machines that do creative work, such as this one. We can get machines to produce paintings. We can get machines to produce sounds and videos. So I think we really need to get used to a future where that's also going to be capable of doing in a machine. If you don't know, like this is a short film called Sunspring. It features Thomas Middleditch. You probably know him as the guy in Silicon Valley. So the script for this short film was completely wrote by machine learning. And it's funny because obviously there's some part, I watched it, it's like 9 minutes long. You should definitely check it out. It's on YouTube. So you can see that there's some parts where like the storyline really doesn't make any sense. There's some random words, but at the same time, you can really you can really follow the storyline. And it really feels like something that could be made by a human, but it wasn't. It's just the machine. Also, Google trained this AI, like they trained an autoencoder algorithm to write this poetry, which is scary because it really makes sense and it's really like teenage angst style. You should definitely check it out as well. It's scary. And also, like Sony used an AI to write a song inspired by the Beatles. What they did is they fed a bunch of music from the Beatles, and this AI was able to write the instrumentals, like the guitar parts and also drums and whatever instruments. And it was all made using machine learning. Again, the song really sounds like the Beatles. The lyrics weren't written by machine learning, but the instrumentals, they were all machine learning. So like in all of these experiments, including mine, you can see that there was always the training phase, which is if we try to make parallels with the way that we create creative work, could be like the phase of creative references, where we reach for references in people that we really admire. But after that, there's some sort of like created unpredictability, because the way machine learning works, like the fact that we don't actually know why it's producing all these results, if we could like try and reach for our creative method of working, it could really be something that's very similar to our human creativity. So that's very interesting, because we can definitely make a parallel with the way that we actually create, with the way that we can get machines to create something for us. And just like in Kosuth's work, like 1 and 3 Chairs, he didn't really make any of these things, as I didn't really make any of the paintings. But there's a meaning to it. Like you can see that all of these means a chair, as in the art there that I did using my computer, it all means art, it all means landscapes. And for me, that's what art is. Art is just making meaning. So whatever you're using to actually create, if you're a developer and you just feel frustrated because you're not doing art anymore, well, good news. You can now get your machine to make it for you. And if it has meaning for you, then it's art. That's what art is for me. What do you think that's art for you? You can check out this project and some other crazy machine learning projects in my GitHub account. And if you like this talk, you can talk to me and reach out to me on Twitter. This is my Twitter handle. You can leave a message. Muchas gracias.